Now, I will start this discussion with explaining supervised learning. Machine learning is a branch of artificial intelligence that enables systems to learn from data, identify patterns, and make decisions with minimum human input. It is broadly classified into supervised learning, where models use labeled data for prediction, and unsupervised learning, where models discover hidden patterns without labels. Algorithms like KNN are effective for instance-based classification, while comparison clustering methods such as k-means, DB-scan, hierarchical clustering, and Gaussian mixture methods group similar data points for pattern discovery. Techniques like dimensionality reduction and matrix factorization further simplify data, enhance efficiency. The choice of method depends on the data, problem, and desired output. Next slide, please. Supervised learning, we use it for training a model using label data, meaning with each input we already know the desired output. Model's goal is just to understand the mapping from input to output so it can make predictions for new data. There are two main tasks: regression and classification. Regression is predicting a continuous number, such as predicting tomorrow's temperature, a stock price, or the amount of rainfall. Where classification is predicting a category, where it's like whether an email is spam or not, or if a tumor is malignant or benign. The term supervised part means the model is guided by a correct answer during training, similar to a how teacher grades homework. Key goal is to learn the mapping from input to output. Next slide, please. Now, supervised learning workflow begins with data collection, gathering relevant examples for the problem. For supervised learning, the labeling is crucial. If the labels are missing or wrong, the models learn incorrectly. Then next comes processing, cleaning missing or incorrect values, encoding categorical features such as red, green to numerical forms, scaling or normalizing numeric features so that large-scale data features don't dominate small-scale ones. Then we split the data set into different sets such as training set, validation set, and test set. Training set to feed the model, validation set to tune hyperparameters and compare models, test set to final evaluation for performance. Optionally, cross-validation can be used to make the most limited data. Finally, after training, we evaluate, deploy into production, and monitor the model's predictions. Next slide, please. Common algorithms and when to use. Different algorithms have different strengths. Linear regression predicts numeric output with a straight line relationship. Logistic regression is for classification and output possibilities. They are fast, interpretable, and great baselines. Tree-based models split the data into branches based on feature thresholds. They naturally handle nonlinear patterns and categorical features, and ensembles like random forest and gradient boosting improve performance. K nearest neighbor predicts by looking at the closest example in the training set. It's intuitive but can be slow for large data sets. Neural network learn highly complex patterns from the large data sets, especially for images, text, or speech. Thank you.
So now let's move on to the unsupervised learning. So unlike the supervised learning, here we do not have any labels in our dataset. That means we have no predefined supervisor or we have no knowledge about the data. So instead of figuring out the correct output, it figure out the hidden patterns or structure in the data of its own. The main goal of unsupervised learning include clustering, where we group together similar data points. Then the dimensionality reduction, which means simplifying the data while still keeping the most important information. Then the density estimation, where we try to understand how the data is distributed. And lastly, the anomaly detection, which is identifying the rare and unusual data points. Some real world examples include grouping the customer's behavior on their shopping behavior, discovering the topics from the large collection of documents, or detecting the frauds even when we don't have the predefined fraud cases. Next slide. So now the clustering and dimensionality reduction. One of the main technique is unsupervised learning is clustering. This is where we divide our data into groups so that the items in the same group are more similar to the other than the items in the other group. Some popular clustering methods are k-means, hierarchical, dbscan, gmm. K-means, which assigns the data points to the nearest cluster center, then adjusts the center until the things settle. Hierarchical clustering builds a sort of family tree on a dendrogram, showing how the clusters relate to each other at different levels. Next, the DB scan, which looks for dense regions of data points and treats the isolated points as noise. And lastly, GMM, which stand for Gaussian mixture models, which assumes which cluster is shaped like Gaussian distribution and gives us the probability of each point's cluster membership. There are many types of dimensionality reduction which simplifies the data. So, firstly, the PCA, which stand for Principal Component Analysis, which finds the direction of the data with the most variance and projects the everything onto this direction. And next is the kernel PCA, which extends this to capture the non-linear relationship. The benefits are huge. Basically, it speeds up computations, removes redundancy, and even help to visualize the high dimensional data in 2D and 3D space. Next slide. Now, another powerful approach of unsupervised learning is matrix factorization. It is used a lot in recommendation system like Netflix, Amazon, Flipkart, where we want to predict what is the user might like, even if they have not never rated them before. So here is an example of matrix factorization, SVD. SVD stands for Singular Value Decomposition, which breaks the large data table into three smaller matrices, which reveals the hidden relationship between the users and the item. Next, the NMF, which stands for Non-Negative Matrix Factorization, keeps everything positive, making it easier to interact, for instance, decomposing an image into meaningful parts of for eyes, nose, and mouth. Next, the matrix compression. It can feel in missing values, such as predicting ratings for items a user has not seen yet. Then we have some generative models. Firstly, the GMM, which stands for Gaussian Mixture Model, which assumes our data is a mixture of Gaussian shaped clusters. And then the LDA, which stands for Latent Dirichlet Allocation. It is specially useful for topic modeling. It assumes which document contains a mix of topics and each topic contains a certain keyword. Overall, these techniques allow us to uncover the deep structures of the data even without any labels and can lead to a powerful prediction and insights. Thank you.
So, good evening, sir. I am Kaustav Poddar, and just now we discussed about supervised and unsupervised learning. So, let's now see a supervised algorithm, which is knowledge tables or KN. So, what is KNN? So, the definition says a lazy learning instant-based algorithm used for classification and regression. So, the core idea is a new data point is classified based on the majority vote of k nearest neighbors. So why does it call lazy learning? It is called lazy learning because there is no training time. It means it doesn't KNN doesn't teach a model separately. It just stores the all data and then when it is time to classify a model, it takes that data and and then chooses some best values and it classifies it. So the some key characteristics are no explicit training phase, as we said, and then stores the whole data set, works well with small data sets. Some useful applications are is used in recommendation system and image diagnosis. So some algorithms are, it is simple, it has no training phase, and it is adaptable to solve many problems. Many problems. So now let's see the how the algorithm actually works. So the first step is choosing the value of k. K means the number of neighbors, and then calculate the distance between query point and all data points, and then select the k nearest points. Classification, we use majority of neighbors labels, and for regression we average out neighbors values. So now how we determine which points are nearest to the query point. So we use some matrix which are equilibrium distance, Manhattan absolute distances, and minus distance formula. So let's now jump into like what are the pros and cons of this algorithm. So the pros are it is easy to understand and implement, as it has no training data set. So it is much faster if the data set is small, and it works for multi-class problem as well, and no model assumptions. And what are the advantages or cons? It is computationally expensive for larger dataset. As we seen that this algorithm calculates the distance with the query point with the all other data points. So if the dataset is large, so it will be computationally expensive, and it is sensitive to irrelevant features and scaling, and performance depends heavily on the k choice. So how can we overcome these problems? So the best practices are we should use some feature scaling, normalization and standardization of the dataset, and we should try different values of k so that we can cross validate and check our output. And we should use some KD tree, ball tree for faster neighbor search in the larger datasets. Thank you.
So, good evening, sir. So now we are diving into the clustering algorithm tools. It's a unsupervised learning machine learning algorithm that help us group similar data point without predefined labels. So imagine walking into a bookstore without any knowing the categories of the books. Clustering is like an assistant who organizes books into sections like mystery, sci-fi, etc. without anyone telling them the genres. Different algorithms can group the same data in different ways. So picking the right one depends on factors like cluster shape, data size, and noise. Our goal is to find the method that naturally captures the structure hidden in our data. Next slide. So here are some popular choices like k-mean clustering, fast and simple, great for round, equally sized cluster, like grouping similar sized apple in a market. Hierarchical clustering. Build a tree-like structure, perfect when you don't know the number of groups upfront. Division clustering. Finds odd shape and handle noise, like spotting irregular shaped coral reefs in the ocean. Gaussian mixture models. Probabilistic allowing overlapping our clusters. Think of people who can belong to both coffee lovers and tea lovers group. And remember, scaling your data before distance-based method can make a big difference. Next slide. So how do we know which algorithm works best? We can use internal metrics when we don't have labels, like the silhouette score, which checks how close items are to their own cluster versus other, or the Davis Gordon index, where lower score means better separation. If labels do exist, external metrics like adjusted rank index can compare the algorithm result to the actual truth. Best practice, which one is best practice? Test multiple algorithms and visualize result. Think of it like trying on outfit before a big event. You need to see what fit best. Next slide. So to conclude, machine learning offers many ways to explore data, from supervised prediction to unsupervised discovery. The right method depends on the problem, data, and the insight we want. Whether it's gaming, division, or other, the key is matching the tool to the task. Thank you.
Points to a given input, the input based on the measure. So it simplifies the effectiveness and make it popular choice in various applications, particularly for pattern recognition and the recommendation system. So here in the diagram, we can see that we have chosen a new data point like pointed by the blue color, and we have some neighbor data point. So here we have chosen four nearest neighbor, three nearest neighbor. So in case of three nearest neighbor, we can see that in the majority, the blue dot can be classified in the green category. So in the next slide, we will talk about the working of the algorithm. So KNN operates on the principle of proximity. So we need to utilize some distance metrics such as Euclidean or Manhattan to find the nearest neighbor. So it computes in very simple steps. First, we select some number of neighbor. Then we compute the distance between the points, and in the majority vote the input data point is classified on the labeled category. And this method allows KNN to adapt dynamically to local data distribution. Some key parameters and considerations. So we have to choose the K value in such a way that we don't get any noise or overfit the data, or we overgeneralize the data, or maybe may underfit the data. So that's why feature scaling is essential in the KNN, and also we use some techniques like normalization and standardization that is used to avoid the bias towards the data. So next, variants and applications. So we have some variants of KNN like weighted KNN where we give some weightage to some data points, and corresponding to that data points we calculate the distance, creating an impact on the data point. And we have adaptive KNN used for specific use cases. Then some real world applications. So we use KNN in disease prediction, e-commerce, and product recommendation systems. Um, and in by leveraging KNN, business can enhance decision-making processes and improve customer experiences. So next up, we have some case study on KNN, which is specified, which is the movie recommendation system. So here we recommend movies to the user based on the ratings from similar user. So here in the table, we can see we have some user and we have a new user, which is the new input data point. So we have some data points x in the x and y axis, and we have some rating on the genre of drama, horror, and romance. So we can see we have chosen the nearest neighbor as 2nn, means we have choosing k as 2. So first we calculate the distance to the all the users from the new user, and we can find that two nearest neighbor is Bob and Alice. So by using the rating given by Bob and Alice, we can see that drama is getting a higher recommendation. So we will recommend the drama movies to the new user. And in the conclusion, we can say K nearest neighbor is a very versatile algorithm applicable in various domains, and we have understood the workings, key parameters, and variants. And also, when applied judiciously, KNN can yield insightful predictions, drive valuable business outcomes, and demonstrating its importance in the analytics landscape.
Focusing on maximum margin classification principle. Now let's understand what is classification in machine learning. So classification is a fundamental task in machine learning focused on categorizing data. The primary goal is to assign new unseen data points to one of several predefined categories or classes. This is achieved by identifying intricate patterns from a prepared training dataset. For example, a classification model can distinguish an email as inbox or spam. This is a supervised learning approach as the models are trained during using data sets where each data point has a correct label or category. So data is transformed into feature vectors, positioning it in a multi-dimensional space. The central challenge is to establish clear boundaries, often hyperplanes, to separate the classes. Once a model is trained, its performance is evaluated using metrics like accuracy and precision. Let's jump to the next slide. Now in this slide we will understand the hyperplane. So at the core of many classification algorithms, including SVMs, is the concept of a hyperplane. It serves as a decision boundary to divide data points into distinct classes within a multi-dimensional space. In 2D space, a hyperplane is a straight line, and in 3D space, it is a flat plane. For spaces with more than 3 dimensions, it remains an abstract boundary that separates data points. And hyperplane is mathematically defined by an equation like w dot x plus b equals to 0. Its position and orientation are determined during the training phase to optimally separate the different classes. When a new data point arrives, the model checks which side of the hyperplane it falls on to assign it to the current class. Now in the next slide, we will understand how many possible separators can be there, and among them which one will be best. So for linearly separable data, where classes can be completed separated by a straight line or plane, there is an infinite number of possible hyperplanes. While each of these could achieve 100% accuracy on the training data, they are not all equally effective for real-world applications. Some hyperplanes create only a small gap or margin to the closest data points, making them highly sensitive to data variations or outliers. A narrow margin significantly increases the risk of misclassifying new unseen data, which can lead to poor generalization. This raises a core question: how do you select the single most robust hyperplane from countless possibilities? So now in this slide we will understand the maximum margin principle. The cornerstone of support vector machines is the maximum margin principle. SVMs identify the hyperplane that separates distinct data classes with the largest possible margin. This margin is the maximum distance between the hyperplane and the closest data points from either class. These closest data points are known as support vectors, and they are what define the optimal boundary. A wider margin leads to superior generalization, ensuring the model performs robustly on new and unseen data. By maximizing this margin, SVMs inherently reduce the risk of overfitting. Now jump to the next slide. So in this slide we will understand the critical data points needed for support vectors. So support vectors are the most crucial data points in support vector machines. They are data points from each class that lie closest to the decision boundary. These points support the hyperplane and directly influence its position and orientation. The distance from these points to the hyperplane dictates the width of the margin itself. Support vectors represent the hardest cases to classify. All other data points, regardless of how numerous they are, do not contribute to the definition of the hyperplane once the support vectors are identified. Now in this slide we can formulate the optimization problem. So the initiative goal of maximizing the margin is translated into a mathematical optimization problem. There, the objective is to determine the optimal parameters of the hyperplane. So in this case, the weight vector W and the bias term B. So the margin between the two parallel hyperplanes is 2 by mod of W. Therefore, maximizing the margin is equivalent to minimizing this W, which for computational convenience is expressed as minimizing half of W square. This minimization is subject to the constraint that every data point x of I is correctly classified. So the constant y of I, which is basically the w dot xi plus b, which should be greater than equals to 1, ensures this. The data points that satisfy this constraint with equality are precisely the support vectors. Now in this slide we will understand why maximum margin really matters and the intuition and benefits. The maximum margin principle offers profound benefits, creating a resilient line. By creating a wide buffer zone, SVMs are more robust to noise and outliers in the training data. This leads to a lower generalization error or unseen data, as the model is less likely to misclassify new examples. A larger margin also enhances classification confidence, as new data points far from the margin are classified with more certainty. Lastly, because the margin is defined by support vectors, the SVMs focus on the most challenging and informative data points, making the algorithm efficient and powerful. Now, let's understand the limitations and extensions of support vector machines. The basic maximal margin classifier, also known as hard margin SVM, requires the data to be perfectly linearly separable, which is rarely a case in the real world. To address this, SVMs have been extended with powerful techniques. Soft margin SVMs allow for some misclassification or violation of the margin, providing flexibility for messy data. The kernel trick is an ingenious technique that allows SVMs to handle nonlinear data separation. Instead of explicitly transforming data into higher dimensional space, The kernel tree implicitly computes the dot product, which enables the SVMs to find a linearly separating hyperplane in that a dimension corresponding to a non-linear boundary in the original space. Now let's understand the summary of the power for maximum margin classification. So in this slide we will understand that SVMs are a robust classification algorithm based on the maximum margin principle. They find the optimal hyperplane to separate classes by maximizing the margin. This process is grounded in a precise mathematical optimization problem. Support vectors are the crucial data points that define this robust boundary. This wider buffer zone created by the maximum margin makes SVMs robust to noise and leads to better generalization on new data. With extensions like the kernel tree and soft margins, SVMs can handle both linear and non-linear data, giving them widespread applicability. Once the model is trained, SVMs are also computationally efficient for prediction.
Our topic is Introduction to Ensemble Learning. So, what is ensemble learning? A powerful technique in machine learning that combines multiple models to achieve superior predictive performance compared to any single model. This approach is crucial for building robust and accurate predictive system across various domains. So, there are the main 3 points, 3 features of ensemble learning. They are the power of many, the ensemble techniques, and presentation roadmap. So, the next slide. There is history of ensemble method in supervised learning. So early foundations, the root of ensemble learning back to the 1960s and 1980s, when researchers began experimenting with combining algorithm to reduce errors. However, it wasn't until 1990s the ensemble methods became formalized with statistical backing. So in 1995, Leo Brain introduced bagging, bootstrap aggregating, and demonstrating that combining models trained on bootstrap data samples could significantly reduce variance. 1996, Freund and Robert Safari developed AdaBoost, showing the combining weak learners would create a highly accurate ensemble by focusing on hard-to-predict instances. So there are theoretical developments. Ensemble learning matured through deeper exploration of bias variance trade-offs. Bagging was shown on reduced variance with increasing bias. Boosting was found to reduce both bias and variance, but at risk of overfitting if not recognized. The next slide is bagging and bootstrap aggregating. From this topic, Akshadip Naha will now continue.
Myself Akashdev, and I will be presenting about the bagging bootstrap aggregating. So what is bagging? And it shortly stands for bootstrap aggregation. It involves multiple instances of the same learning algorithm on different random subsets of the training data, then combining their predictions, typically through averaging for regression or voting for classification. So here are some random sets where models are trained on bootstrap subsets of the original dataset, which means sampling with replacement. It helps in diversity among models. Notable example we have such as random forest, where multiple decision trees are built and results are aggregated. And the key advantages is that it reduces variance in predictions, making models less prone to overfitting, especially with complex base learners like decision trees. Next slide, please. So here we have the visualization of the entire process. We can observe that how the original database is resampled to create multiple bootstrap subsets, each used to train an independent model. So here are the classification tasks and also the regression tasks, which are done by the majority and the individual models, leading to a stable and accurate result. Next. So here we learn about the sequential improvement of the boosting process. Basically, it is a process in which the weak learners are converted into strong learners, and each model in the sequence focuses on the errors made by the predecessor. The training in each subsequent model focuses on data points that were misclassified or poorly predicted by the preceding models, and the processes that are involved in the algorithm are AdaBoost, gradient boosting, and the highly optimized XGBoost. And the primary advantages is that it reduces biases by making models more accurate by focusing on different examples and adapting to complex patterns in data. Next slide. Here is a model 1, 2, 3 visualized format of the boosting process. We can note that how each model in the sequence is built to give more weight to the data points that previous models struggled to, leading to a refined and more accurate overall predictor. This iterative correcting mechanism allows boosting algorithms to receive high accuracy, particularly in situations where initial models might have high bias. Next. Here is a comparison between the two processes that we have learned till now. One is bagging and the other is boosting. In bagging, the primary benefit which we get is the reduction of the variance, whereas in boosting, it is the bias which is being reduced. Models are trained in parallel for bagging, whereas it is trained sequentially for the boosting process. Ideal when base models are prone to overfitting is in bagging, and in boosting, it is useful for reducing bias and overall improvement. Next. So here is stacking, the third assemble method, which is also known as the assemble of assembles. And it is basically termed as stack generalization. For it takes the predictions of multiple diverse base models and uses a separate meta model for learner to learn how optimally combine these predictions for the output. Base models include decision trees, support vector meshes, etc. And in meta models, the model is trained for the outputs of the base model. And the synergistic advantage is that it surpasses any single base model or even simple assemble techniques like bagging or boosting. And the next slide will be presented by Swami.
Hello, so this is Ankshuk Banerjee.
Ankshuk.
I'm presenting a stacking process visualized. The diagram illustrates the sophisticated workflow of stacking. You can see how raw data is fed into multiple diverse base models, whose predictions then form a new dataset for the meta model to learn from, ultimately generating the final prediction. The hierarchical approach allows stacking to capture complex nonlinear relationship between the base model's prediction and true labels, leading to highly accurate and robust models. Can you put the next slide, please? A case study predicting the customer churn. Incredibly powerful in real-world application. Take customer churn prediction in telecommunication. This allows proactive intervention, significantly impacting revenue. Models often struggle with complex nonlinear patterns and imbalanced churn data. How does ensemble solution help this? Random forest bagging or gradient boosting can dramatically improve accuracy by combining weaker learners. And the key benefits are ensemble models provide robust, accurate predictions, enabling precise targeting of at-risk customers and better understanding of churn drivers. Next slide, please. So this is the mainly summary of ensemble methods, that is the method and the combination strategies and the main benefits and overfitting risks and the speed. Bagging is average and the main benefit it reduces variance, and overfitting risk is that it is slow and the speed is fast. Whereas on boosting it is sequential, focuses on errors, and it is reduces bias and variance. It's medium high and slow. Stacking, on the other hand, is a meta model on multiple model outputs, leverages model diversity. It's medium in risk and its speed is at a medium pace. And the last slide, please. And at last, we'd like to conclude, and the key takeaways are that bagging, boosting, and stacking represent powerful strategies for enhancing machine learning models' performance by cleverly combining multiple individual learners. Bagging at first is a variance reduction, effective in mitigating overfitting by averaging predictions from models trained on diverse datasets. Boosting, on the other hand, minimizes the bias through sequential training, where each model focuses on correcting the errors of its predecessors. And at last, stacking, synergetic combinations, leverages the unique strengths of various models via a meta model, often yielding superior predictive accuracy. Thank you, sir, and the references are given below. That is all.
Comic model of Rajdeep Chaudhary and Mohit Bhattacharya. Our topic is optimizing linear regression model. assumption, feature selection, and regularization techniques. Next, first slide. Introduction to regression. Linear regression is a supervised machine learning algorithm used to predict continuous target variable based on more predictions. The core idea is method models the relationship between variables using linear equation and minimize prediction errors. Why does it matter? Simple and interpretable, foundational for understanding advanced ML models, widely applied in economics, healthcare, and marketing. Next slide. Let's talk about the brief history of linear regression. This is early founded in Adrian Marie introduced method of least squares. Advancement done by Carl Friedrich Gauss applied last square to astronomical data. In 20th century, it is used extensively in statistics for economics forecasting and scientific research. In modern day, forms the base for many advanced machine learning algorithms enhanced with feature selection and regulation techniques to address complex real-world data elements. Next slide. From it made it make it full screen. Make it full screen. No. Make it full screen. Okay. Fine. Just leave it there. Linear regression. The basics of regression. Linear regression is a foundational supervised learning algorithm used to predict a continuous target variable based on one or more independent variables. It models the relationship between variable by fitting the linear equation to observe the data. It has predictive power. It predicts a numerical output from the linear relationship. The core equation is y equals to beta 0 plus beta 1 into x1 and continuation. Beta values are the models of coefficients. The goal is minimize the prediction error. Next slide. Show me next slide.
Show me go out from full screen mode and then change the slide. It's not working if you change it in the full screen.
Ordinary OLS, finding the optimal coefficient. OLS is the most common method for estimating the coefficients of linear regression. It works by minimizing the sum of the squared differences between the observed values and the values predicted by the model. Error minimization. The OLS measures the error between prediction and actual values, aiming to minimize the sum of squared errors. This ensures that the best fit line is found. The OLS formula is beta equals to x to the power t into x to the power minus 1 x to the power t into y. The matrix algebra divides the unique set of coefficient that minimizes the square terms. The key assumptions are OLS perform optimally when the data meets linearity, independence of error, and no multicollinearity. The next slide will be presented by my friend Mohan.
Practical application of linear regression. Linear regression is ideal when relationships are roughly linear and interpretability matters. For example, predicting house price based on size, number of bedrooms, and locations, or estimating salaries from experience, education, and industry. Next slide. Overfitting and regularization. Overfittings happen when a model learns noise from the training data and fails to generalize to new data. This often occurs when with too many features or overly complex models. Regularization helps by large coefficients, simplifying the model and improving generalization. Next, reach regression, L2 penalty. Reach regression or L2 regularization adds a penalty term to swing coefficients towards 0 It stabilizes the model, especially when features are highly correlated, ensuring reliable predictions even with many features. Next slide.
Good evening, sir. My name is Rajdeep Chaudhary, and I'll be talking about the further slides. The next slide we have is about lasso regression or L1 penalty. The key difference between the lasso and the ridge penalty is that lasso uses an L1 penalty, meaning it adds the sum of the absolute values of the coefficients to the loss function. Unlike ridge, which only shrinks coefficients, lasso can actually shrink coefficients exactly to zero, which means it doesn't just reduce their influence, it completely removes irrelevant features from the model. This makes lasso a powerful tool for feature selection and for building models that are simpler and easier to interpret. Next slide. Next, we have the elastic net, which combines both the L1 penalty from lasso and the L2 penalty from ridge in its loss function. This allows it to not only shrink coefficients to prevent overfitting, but also set some coefficients to zero for feature selection. This is especially useful when we have groups of correlated features, in which case some will be dropped, others will be reduced, giving you a balanced, more reliable model. And in the case of elastic net, we control the strength of the penalties using a hyperparameter lambda. If lambda is too small, we risk overfitting, behaving like normal regression. If lambda is too large, we risk underfitting. So we use cross-validation to find the sweet spot that balances bias and variance. Next slide. Next we have the what and why of feature selection. Feature selection means the process of choosing the most relevant predictors for our regression model. Why is this important? Because it improves accuracy by removing irrelevant or noisy features, reduces overfitting, helping the model generalize better, and makes our models more interpretable and faster to run. In linear regression, too many predictors can cause multicollinearity and unstable coefficients. Feature selection ensures we only keep features with the highest predictive power. There are three main approaches to this: filter methods, wrapper methods, and embedded methods. And feature selection is so we see that feature selection is essential for building models that are both accurate and efficient. Thank you. Next.
Good evening, sir. I am Mayur Bhattacharya and I will be presenting the rest of the presentation. So, feature selection approaches in linear regression. First is filter methods, which is model independent. It uses statistical tests before training, like ANOVA, mutual information, and Pearson correlation. Pros are it's fast and simple, while it ignores feature interactions. Second, we have wrapper methods, which is model-based search. Evaluates subsets using model performance. It has forward selection, backwards elimination, and stepwise. Pros are consider interactions which are ignored by filter methods, but it's slower and has risk of overfitting. Third, we have embedded methods during training. Feature selection happens in model fitting that we discussed, like L1, L2, and elastic net. Pros are it's efficient and handles multicollinearity. Next slide, please. Assumptions, how to validate linearity. Predictors and response should have a straight line relationship. We can check this via a scatter plot or residual plots. Independence of errors. Residuals should not be correlated. We can check this with a Durbin-Watson test. Homoscedasticity. Constant variance of errors across predictions. Check residuals versus fitted plot. Normality of errors. Residuals follow a normal distribution. We can check this with a QQ plot or a Shapiro-Wilk test. And lastly, no multicollinearity. Predictors are not highly correlated. This is important because multicollinearity means one change in feature can result in a very big error. So we can check this with a variance inflation factor, VIF, or a correlation matrix. Next slide, please. Violations and their remedies. When these assumptions are violated, the model's accuracy and interpretability can decline. Non-linearity can be corrected with a transformation or polynomial features, while auto-correlated errors often require models like GLS or ARIMA. If the error variance is unequal, heteroscedasticity, methods like weighted least squares or transforming the dependent variable can help. Non-normal errors may be handled through bootstrapping or transformations, and multicollinearity can be reduced by removing or combining correlated features or using regularization methods such as ridge or lasso regression. Next slide, please. In summary, linear regression, which the main topic of this presentation, it predicts continuous outcomes using a simple yet powerful mathematical model. Optimization, it is achieved through validating assumptions, careful feature selection, and regularization methods like ridge, lasso, and elastic net. The key takeaways from this presentation are: understand assumptions for accurate predictions, avoid overfitting using regularization, select the most irrelevant features for better performance and interpretability. Real-world impact. From predicting house prices to improving business decisions, linear regression remains an essential tool in data science. Thank you, and that is all for this for our group and this presentation. Thank you.
We'll discuss about supervised and unsupervised learning, KNN, and clustering comparison. So, introduction to supervised learning. First is definition and analogy. A machine learning approach where algorithms learn from labeled datasets. Each training example has input features and the correct output or label. The model maps input to outputs improves the prediction over time. Example: we can detect detect spam emails using this. Weather forecast, credit score prediction, and handwritten digit recognition. History. In 50s to 1960s, Frank Rosenblatt in 1958 emerged with the perceptron. He created one of the first supervised learning algorithms. And then is 1990s, statistical learning theory. Vapnik and Chervonenkis provided strong theoretical foundation for this algorithm. Nowadays in present day, widely applied in finance, healthcare, and NLP and image recognition with the rise of big data sets and deep learning. Next slide, please. Supervised learning. Supervised learning is when we train a model using data sets and that already has levels, meaning one for each input we know the desired output. The model goal is to learn the mapping from inputs, and to outputs so it can make predictions under new data. There are two main tasks: regression and classification. In regression, predicting a continuous number like predicting tomorrow's temperature, stock price, amount of how much rainfall it will be. And classification is predicting a category like whether email is a spam or not. The supervised part means the model is guided by the correct answers during training, similar to when a teacher grades a homework. He will learn a mapping from inputs to outputs. So, supervised learning workflow. The workflow begins with data collection, gathering relevant example for the problem. For supervised learning, labeling is crucial. If labels are missed or wrong, the model learns incorrectly and the output will be wrong. Next come pre-processing. Pre-processing has three steps like cleaning missing or incorrect values, encoding categories and categories features, like we have to turn the color from word to numerical form. Scaling and normalizing numeric features so that the large scale features don't dominate small scale ones. Then we split the datasets into three sets: training set, validation set, and test set. Training set is to fit the model. Validation set is to tune hyper parameters and compare models. Test set is the final evaluation of the performance of the algorithm. Optionally, cross-validation can be used to make the most limited data. And finally, after training, we have to evaluate and deploy into production and monitor the model's prediction. That's all from me. My group member will start from the next slide.
Hello, good afternoon, sir. My name is Monobruto Ghosh, and the topic of the presentation will be Introduction to this Unsupervised Learning. So, if we go about the definition and the analogy, then unsupervised learning is a type of the machine learning where the model is not given with unlabeled data and must find hidden patterns, structures, or relationship without explicit guidance. Unlike supervised learning, there are no correct output labels to learn from. The system organizes the data based solely on its features. There are some examples like customer segmentation in marketing, grouping similar news articles, detecting abnormal network traffic patterns, topic in modeling in text data. There are also some key goals of the unsupervised learning, which are discover structure in data, group similar data points, which is also known as clustering, reducing data dimensions for simplification or visualization, and also to detect anomalies. If we go about the history of the unsupervised learning, so in 1950s to 60s, early AI research was focused on symbolic learning, but clustering methods like k-means, MacMean, that was invented in 1967, which has emerged as statistical pattern of the recognition tools. In 70s to 80s, the development of self-organizing maps like Cohonen, which is in 1982, and association rule mining concept have come over. In 1990s, market-based analysis popularized, and now 2000 to 2000 present is high-dimensional data analysis with PCA, TSNE, and deep learning based on autoencoders also have been introduced to the modern-day science. Next slide, please. So there are some types of unsupervised learning. The first type is known as clustering, which is actually grouping the similar data points together. There are some examples like k-means, hierarchical clustering, or DBA scan. There are so many examples. There are applications of unsupervised learning as well, like customer segmentation, image grouping, genetic data analysis, and etc. If we come about the next is dimensionality reduction, which is actually compressing the data into fewer dimensions while retaining the essential information. There are some examples like PCA, which is principal component analysis, autoencoders, etc. Application wise, if we say like data visualization, noise reduction, and speeding of algorithms, etc. If we go about the anomaly detection, that is actually finding unusual or rare patterns, and like with examples in fraud detection, network security as well. These are some common use cases I have already mentioned. The goal is always to find hidden structures, patterns, or grouping present in the system. Next slide, please. There are some common algorithms we used, which is linear regression that actually predicts the output in a straight line relationship. And if we come about the next, which is logistic regression, which is actually a classification and output probability process. This is actually fast, interpretable, and also great for the baselines as well. There are some tree-based models which actually splits the data into branches and bases like features thresholds. Actually, they naturally handle the nonlinear patterns and also categorical features as well. And also assembles like random forest or gradient boosting, improving performances as well. The next is the most popular, the k nearest neighbors, which is KNN, which actually predicts by looking at the closest example in the training set given. And if we call out the features, it is already intuitive but can be slow where the data set is already large. If we come out the last common algorithm, which is neural networks, which is actually learns about the highly complex patterns, like when we have large data set, especially for the image, text, or speech, or something like that. This was for me my part. From here, my fellow team member will continue.
Hello, sir. Myself, Abhijit. From this slide, I will be continuing. So here is introduction to clustering, definition and analogy. An unsupervised learning technique for grouping similar data points into clusters, where points in the same cluster are more similar to each other than to points in other clusters. For an example, like in the graph given below, we can clearly see that the circular cluster formatting the basic of distance. Like here are the similar type of data are branching together. So that is the example. Now is cluster formatting method. Here are many types of clustering formatting method are there. Firstly, density based. In this method, the cluster are formed as dense region. The advantage of this method is they have good accuracy as well good ability to merge to cluster. For example, density based spatial clustering of application with noise or DB scan. Ordering point to identify clustering structure or optics. Second is hierarchical based. In this method, the clusters are formed as a tree-type structure based on the hierarchy. They have two categorical, namely algorithm bottom-up approach and diffusive or top-down approach. For example, clustering representative balance iterative reducing clustering using hierarchy. Partitioning based. In this method, the clusters are formed by partitioning the object into k clusters. Number of clusters will be equal to the number of partitions. K means clustering large application based upon random search. Or finally, grid based. In this method, the clusters are formed as a grid-like structure. The advantage of this method is that all the clustering operation done on this grid as first as dependent on the number of data objects. For example, statistical information grid or string clustering in Quest or SlickView. Popular clustering method and when to use. Like K means algorithm, fast, simple, and work best spatial cluster for similar size data. Hierarchical, build dendrogram and no need to choose number of cluster upfront. DB scan, detect irregular shapes, handles noise well, needs density parameters. Gaussian matrix model or GMM, probabilistic allow overlapping clusters. And finally, use clustering before applying distance-based method like k-means. From next slide, our friend Barin will be continuing.
Good evening, sir. I am Barin Ghosh and I'll be continuing from KNN or K nearest neighbors. Thank you, Abhijit. Now moving ahead from clustering, let's talk about another fundamental algorithm in machine learning, K nearest neighbors or KNN. KNN is a lazy learning instance-based algorithm used for both classification and regression tasks. In simple terms, it looks at the closest data point to make a decision. For example, in classification, a new data point is assigned to the majority class among its nearest neighbors. For regression, it simply averages their values. What makes KNN applying is its simplicity and versatility. It's non-parametric, meaning it doesn't assume any prior data distribution, making it suitable for a wide range of real-world applications, from pattern recognition and recommendation systems to detections. Next slide. Hello. Yes. Now let us see how KNN actually works. First, we choose a value of k which represents the number of slides to consider. Then we calculate the distance between our point and the neighbors. Then we calculate the distance between our query point and all other data points in the dataset. Common distance metric include Euclidean distance, Manhattan distance, and Minkowski. Euclidean distance is the straight line distance, Manhattan is sum of the absolute difference, and Minkowski a generalized version. Once distance are calculated, we select the k closest points. For classification, we check the majority class among these points. For regression, we take the average, and just like that, the prediction is made. No complex training phase, just direct computation. Next slide. Now to summarize, machine learning techniques can broadly be classified as supervised, unsupervised, or semi-supervised. KNN is supervised learning method, meaning it works on labeled data, but it can also blend into semi-supervised setting when the dataset contains a mix of labeled and unlabeled examples. Next slide. In conclusion, machine learning offers a wide variety of approach from prediction to pattern discovery. Choosing the right method, whether it's KNN clustering or dimensionality reduction, depends entirely on your dataset, the nature of your problem, and the kind of insights you are aiming for. Thank you, sir.
Hello, sir. So the topic of our group is supervised learning, regression, classification. And the member of our group are Anurag Singh, Payal Pal, Orpon Pramani, and myself, Ayushi Dev. So moving towards the next slide. What is supervised learning? So before we know about supervised learning, we have to know what is machine learning. Machine learning is a field of artificial intelligence where systems learn from data to identify patterns and make predictions without being explicitly programmed. And a core type of machine learning that uses labeled data to train a model is supervised learning. The data is both input and the correct output, which allows the model to learn and relationship between them. This is primarily split into two main tasks. As we can see, it's regression and classification. Regression is predicting a continuous value, like predicting a car's price based on its features. And the classification is like predicting a category, which is classifying an email like spam or not spam. So moving to the next slide. A brief history of supervised learning. As we can see, the origins of supervised learning can be traced back to the mid-20th century. A historical moment was the development of the perceptron by Frank Rosenblatt in 1958. It was a pioneering algorithm for binary classification, which used a labeled dataset to learn a simple decision boundary. However, the progress was slow due to limited computational power and data at that time. In the 1960s to 70s, the statistical methods like linear regression and Bayesian classifiers became popular for predictive modeling. And in the 1980s to 90s, we saw the rise of algorithms such as decision trees and support vector machines, which are also known as SVMs, offering better accuracy for complex datasets. And in the 2000s, the availability of massive datasets and powerful computers led to enable methods like random forests and deep learning models that revolutionize tasks like image and speech recognition. Today, the supervised learning blends statistical principles with AI, driving intelligent applications in nearly every industry. So in the next slide, we will be discussing overfitting and underfitting, which is high bias versus high variance. When we train a machine learning model, we must find a balance between simplicity and complexity. This is where the concept of underfitting and overfitting comes in. Underfitting, or the high bias, occurs when a model is too simple. It fails to capture the essential pattern in the data and performs poorly on both the data it is trained on and any new data, unseen data. A simple analogy is like we can think it of as a student who doesn't study at all and fails both their practice and final exams. Overfitting or high variance. It is just opposite of the underfitting problem. This happens when the model is too complex and learns the noise and random fluctuation in the training data rather than just the core signal. We can think it of as like a student who memorizes answer for a practice test but then struggles when the questions are slightly different from the real exam. Moving to the next slide. Finding optimal model complexity, bias variance trade-off. The goal is to find the optimal model complexity by navigating what is known as bias variance trade-off. A model with low complexity will have high bias and low variance. A model with high complexity will have low bias but high variance. And in the middle, the optimal model is one that strikes a balance between bias and variance to minimize the overall error. We can achieve this balance using several techniques such as cross-validation, regularization like L1 and L2, and early stopping. These methods help ensure the model generalizes well and prevents it from becoming overly complex. So the next slide will be presented by other members of my group.
Class imbalance. That is when one class is a rarity. Class imbalance happens when one class in the dataset has far fewer samples than the others. This is common in domains like fraud detection, medical diagnosis, or spam filtering, where positive class is rare as compared to the negative one. If the dataset is heavily imbalanced, a model can achieve high accuracy simply by predicting the majority class every time. Yet it will completely fail to detect the rare but important minority cases. So it is a very genuine problem which is faced. And if it fails to detect the minority cases, the standard accuracy becomes misleading. Moreover, the model doesn't learn enough about the characteristics of the minority class, leading to the poor real-world performance. So we can use better matrices. Instead of relying on accuracy, we use confusion matrix, which shows the counts of true positives, true negatives, and false negatives, giving a clearer performance breakdown. Precision and recall. Precision tells us how many predicted positives were actually correct. The F1 score, which is the harmonic mean of precision and recall, and also the AUC ROC curve, which measures how well the model distinguishes between classes across different thresholds. Next slide, please. Now we are discussing about the techniques for balancing classes, that is, the strategies for a fair fight. When dealing with class imbalance, our goal is to make the dataset more balanced so the model learns both classes effectively. There are two main strategies that are used. One is the data level approach and the other is the algorithm level approach. The data level approach, which is often called pre-sampling, it has three main points: the undersampling, oversampling, and SMOT, that is the synthetic minority oversampling technique. In undersampling, we remove some samples from the majority class so that both classes are closer in size. While in oversampling, we duplicate samples from minority class to match the majority list. And in SMOT, instead of copying data, it generates new synthetic minority examples by interpolating between the existing ones. This avoids duplication and gives the model more variety. Now, looking forward to the algorithm level approaches, uh, they can be of two types: the cost sensitive learning and the appropriate algorithms. The appropriate sorry, the cost sensitive learning algorithm is told to penalize mistakes on the minority class more heavily, so it focuses on correctly predicting those rare cases, while the appropriate algorithms like decision trees or random forest naturally handles imbalance better by focusing on splitting data to capture minority patterns. So that's all. The next slide will be presented by my fellow member.
Hello, sir. I am Anurag Singh, role 43, and I'll be talking about model interpretability versus accuracy. In machine learning, there is often a trade off between understanding a model and getting the best possible accuracy. White box models like in linear regression and decision trees are easy to interpret, in which we can clearly see why they made a prediction, but they may not always give top performance. Black box models like deep neural networks and gradient boostings often produce higher accuracy but are harder to explain. Choosing between them depends on the application and the need for transparency. Next, moving on to the next slide. This is where explainable AI or XAI comes in. It's about opening up the black box so we can understand complex models. Interpretability matters for three main reasons. First, trust and accountability. If a medical AI system recommends a treatment, doctor needs to know why so they can trust and verify it. Second, regulatory compliance. Laws like GDPR give people the right to explanation for automated decisions that affect them. Third is debugging and improvement. If our model makes mistakes, understanding its reasoning helps us fix those errors. Techniques like line and shape are used to break down predictions. For example, if a loan application is rejected, shape values can show how much each factor like income, credit score, or employment history contributed to that decision. We can use powerful black box models while still giving clear, human-friendly explanation, which is essential in high-stakes fields like healthcare, finance, and law enforcement. Thank you. Next slide will be presented by Arth.
Thank you. Myself, Abham Pramanik. My roll number is 41. Let me tell you about the transfer learning. Transfer learning is a technique where we take a model trained on a large general dataset and adapt it to a new related problem. Let me tell you with a case study. Medical image classification problem. Training a deep learning model to classify different type of skin cancer is extremely challenging due to limited high quality data and massive conceptual cost. Solution. Transfer learning starts with a pre-trained model. We use a powerful model like ResNet 50 which has already learned fundamental features from a huge dataset of general image. Adaptation and then we replace the final layer from the new task and then train only that part. Thank you. The next slide. Applying transfer layer. The process of transfer layer has four main steps. First, load a pre-transfer model by removing its final output layer, then freezing layer. Secondly, freeze the early layer so that the learned features are preserved. Third, adding new layer. Adding new layer that matches our specific problem. Finally, train only those new layer into on a small data set. The approach works efficiently well in fields like computer vision and natural language processing where large and general models already exist. The next slide. Let me conclude the whole PPT. To summarize, we have covered the basic of supervision learning in history and the challenges of overfitting and underfitting and class imbalance. We discussed the trade-off between the interpretability and accuracy and how expandable AI can bridge that gap. Finally, we saw how transfer learning can help achieve high accuracy efficiently with the right technique. Supervised learning and can be applied efficiently to a wide range of real-world problems. Thank you, sir.
To give a presentation about a crucial concept in machine learning, overfitting and underfitting, and finding the optimal model complexity. The first slide is mastering model complexity. So what is the biggest challenge in machine learning? It's achieving robust performance which hinges on a model's ability to generalize effectively to unseen data. In this presentation, we are going to dive deep into the critical balance of model complexity. We will define the two main pitfalls or problems, which are overfitting and underfitting, examining their causes and effects, and most importantly, equip ourselves with the practical strategies for detecting and fixing them. This isn't a new problem. As we can see in the slide, like the struggle with model complexity is ancient. Early astronomers have problems that were too simple and underfit planetary orbits, while later models tried to explain every single wobble ended up overfitting the data. The core idea is rooted in the 14th century principle of Occam's razor, which tells us that a simpler is usually better. The term overfitting itself was coined with the rise of modern computers, and the problem was formally defined in 1992 through bias variance trade-off, which we will discuss in detail later. So what is underfitting? Let's start with the first problem, underfitting. Underfitting occurs when a model is too simplistic to capture the fundamental pattern in the data. This means it performs poorly not only on new data but also on the data it was trained on. The key characteristics of the underfit models are it has high bias, which means the model makes strong incorrect assumptions about the data. It has low variance, which means it's not sensitive to the training data. Changing the data a bit won't impact the model much. And poor performance, it has low accuracy on both the training and test data set. And the common causes of underfitting are insufficient features, overly simplified algorithm, and insufficient training. Now if we look at the graph on the right, we can see a perfect visual of underfitting. The blue dot represents the actual data which clearly follows a sine wave like pattern. The red line is our predicted model, a simple straight line. As you can see, the linear model completely fails to represent the true complexity of the data, leading to significant error and demonstrating a classic case of underfitting. Now overfitting. On the other side of the spectrum, we have overfitting. Overfitting happens when a model learns the training data too precisely, to the point where it starts memorizing the noise and outliers instead of the real underlying pattern. It's like memorizing a textbook's typos and all, but being unable to apply that knowledge in a new situation. Its key characteristics are low bias, which means it makes very simplifying assumptions. Then high variance, the model is highly sensitive to a small fluctuation in the training data. Then performance discrepancy, this is the biggest giveaway. Excellent accuracy on training data but significantly poor performance on new unseen test data. And the common causes of overfitting are excessive model complexity, too many features, overtraining, and limited data. Now if we look at the image on the right, we can see a graph. The blue dots are our data points with some random noise. The dashed black line shows the ideal true pattern. Now look at the solid red line. That's our overfit model. Now notice how this highly complex weakly curved contours is said to pass through every single training point, including the noise. While it looks perfect on a specific data, you can imagine that its erratic wiggle will lead to high prediction error for any new data point, showing its inability to generalize. Then the bias variance trade-off. This brings us to the core concept that governs model complexity, the bias variance trade-off. Achieving the best model performance requires us to carefully navigate the trade-off to minimize our total error. Let's quickly define the component again. Bias, which is the error from a model being too simple. High bias led to underfitting. Variance, which is the error from a model being too sensitive to the training data. High variance lead to overfitting. The total generalization error of a model can be broken down into this equation. Total error equals to bias square plus variance plus irreducible error. And irreducible error is the noise in the data itself that cannot be reduced by any other model. Now if we look at the right side, we can see a U-shaped curve. On the left side of the graph where model completely is low, the bias is high. The red line, the variance is low. This is a region of underfitting. As we move to the right side, the increasing model complexity, the bias drop, but the variance increases dramatically. The blue line, this is a region of overfitting. The sweet spot in the middle where the black line representing the total error is at its lowest point. This is where we find the optimal complexity and the best possible model performance. Then finding the optimal model complexity. So how do we practically find that sweet spot? This slide will give us the roadmap. The steps to find the optimal complexity are: at first we start simple, then use validation data to track training and validation error, and then find where both errors are low and close, which is the sweet spot in the bias variance trade-off. Then apply regularization to control complexity. Then use cross validation for a stable performance estimate, and then analyze learning curves to detect if the error gap is widening, which means overfitting, or if both errors are high, which means underfitting. Our goal is to achieve low bias and low variance, creating a model that generalizes well. Now let us look at the diagram of the overfitting iceberg. It metaphors so that the topic which are currently discussing, the bias variance trade-off and the conventional prevention are just the tip of the iceberg, which is called a classical regime. Below the surface, in the modern deep learning regime, we need to rethink overfitting and expand our understanding to effectively manage it in today's complex model. Detecting underfitting and overfitting. Before we can fix this problem, we need to diagnose them. Detecting underfitting and overfitting is a crucial skill. The primary method is to compare the model's performance on the training data with its performance and a separate validation or test dataset. Here are the critical indicators: underfitting indicators and overfitting indicators. The underfitting indicators, the model show low training accuracy. The test accuracy is also low and importantly very similar to the training accuracy. This signals high bias and low variance. And the overfitting indicators, the model achieves very high training accuracy. It has essentially memorized the training data. However, there is much lower test accuracy. A significant drop in performance on unseen data. This indicates low bias and high variance. We have three key detection methods: learning curve, cross validation, and validation loss trend. In the learning curve, these plots track performance as a training progress. With overfitting, the training score stays high while validation score plateaus or drop, creating a growing gap. With underfitting, both score converges at low value. And the cross validation. This robust technique trains the model on multiple subsets of data. Consistent poor performance across all fold points to underfitting. Highly varying performance across fold suggests overfitting, as the model is too sensitive to the specific training subset. Then validation loss trend. When training neural network will monitor the loss, training loss keep decreasing while validating loss start to increase. The model is overfitting by learning noise. This is a key signal for early stopping. If both remain high, it's underfitting. Then the strategies to avoid underfitting. Once we have diagnosed underfitting, how do we fix it? When our model is too simple, we need to increase its capacity to learn. Here are the key strategies. First, increasing model complexity. This is most direct approach. We can switch to more powerful algorithm like moving from linear regression to polynomial regression or from a single tree to a random forest. For neural network, we can add more layers on neuron. Then by adding more features, an underfit model may be information stuck. We can introduce additional relevant input features. We can also use feature engineering to create new, more information features from existing one. Then by increasing training time, for iterative models like neural network, we may simply need to train longer to allow the model to converge. However, we must be careful not to overtrain and cause overfitting. Then by regularization. Regularization technique penalize model complexity to prevent overfitting. If we have too much regularization, it can cause underfitting. In this case, we should reduce the regularization strength. and then we can also ensure sufficient data quality. While more quality is often good, clean and representative data is essential. Poor data quality with issues like missing values or incorrect label can prevent even a complex model from learning properly. Then the strategies to avoid overfitting. Now for the opposite problem, how to combat overfitting. When your model memorizes not this technique will help it generalize data by reducing its complexity or its sensitivity to the training data. At first, regularization technique. These are powerful tools L1, lasso and L2, reach. Regularization add a penalty for large coefficient values which simplifies the model. L1 can also perform automatic feature selection. Dropout is a technique for neural network where a random percentage of neurons are switched off during training, preventing them from becoming too dependent. Then reducing model complexity. This is inverse of what we do for underfitting. We use simpler models. For neural network, reducing the number of layers or neurons. For decision tree, we can limit their depth through pruning. Then cross-validation. Using k-fold cross-validation to get a more robust estimate of how our model will perform on unseen data. This is crucial for hyperparameter tuning and selecting a model that truly generalized well. Then early stopping. As you saw earlier, we should monitor the model performance on a validation set during training. Stop training when the validation errors start to increase, even if the training error is still going down. This prevents the model from learning noise. Then by increasing training data, this is one of the most effective method. The more diverse data a model sees, the better it will learn the true pattern. If we can get more data, we can use data augmentation with creates a synthetic data by rotating or translating image. For example, to increase data set size. Then there are feature selection. In feature selection, we simplify the model stack by identifying and removing irrelevant or reluctant features. This reduces the chances of model learning from noise. Then finding the optimal model complexity. We have discussed this earlier. So now let's move on to the case study. In this case study, we will predict the house prices. So here are the graph on the side. We can perfectly illustrate our three different scenarios. The underfit model. Imagine we say simple linear regression with only one feature. The model will have high training and test error because a straight line can capture the complex housing market. This is directly correspond to the first image we see, labeled underfit, where the straight line is clearly a poor fit for the data. Then there is overfit model. Now imagine we use a 10-degree polynomial model. It will have almost zero training error because it memorizes every data point, including noise, but its prediction on new data will be wildly inaccurate. This is shown perfectly in the third image, labeled overfitting, where the line is described as close fitting, too good to be true because it weakly erratically to hit every single point. In the optimal model, finally we can see a third-degree polynomial with a regularization. This model would have low training errors and similarly low test errors, showing it has generalized well. This ideal scenario is depicted in a middle image appropriately, where the curve smoothly captures the generalized trend of the data without memorizing the noise. This case study show the finding the right balance is everything. A model is that is too simple misses key information, while one is that complex get lost in the noise. Then the conclusion. To conclusion, let's summarize the key takeaways. We have defined underfitting as a model that is too simple, suffering from a high bias and performing poorly on all data. Think of it as a simplistic explanation for a complex problem. We have defined overfitting as a model that learns the training data, including its noise, too well. It has high variance, leading to excellent performance on training data, but poor performance on unseen data. This is like memorizing answer without understanding the concept. So
If we consider the first as 0 and at position as 6, the values of the strings are different.